Hydrogen. It's literally the most common element in the entire universe. It fuels the stars, and for us down here, it represents a huge hope for clean energy. But there's a catch, and it's a really big one. How in the world do you store it? Today, we are diving deep into that very challenge, trying to bottle to cloud.
Right? It seems kind of strange. This stuff is everywhere, but actually getting it to where we need it and having it ready when we need it, well, that's incredibly difficult. So what is it that makes storing the universe's #1 element such a massive headache?
So let's break this down. On the one hand, hydrogen is a potential game changer for decarbonizing, well, everything. But on the other hand, it has this one fundamental problem that just makes it a nightmare to handle.
And here it is. This is hydrogen's kryptonite. At just normal atmospheric pressure, the air all around us right now, hydrogen has a density of just 0.083 kilograms per cubic meter. That's practically nothing. It really is like trying to bottle a cloud. So to get any useful amount of energy, you have to do something extreme. Either you need a gigantic container, you need to use immense pressure, or you have to get it cryogenically cold.
Okay, so how do we tackle this problem on a scale we can all relate to, like a car? Let's look at the incredible engineering it takes to cram enough hydrogen into a vehicle to give it a practical driving range.
The hydrogen tank has been through quite an evolution, let me tell you. We started with what are called Type 1 tanks, basically heavy all-metal cylinders. They could only handle about 200 bar of pressure. Now, just for context, your car tires may be 2.5 bar, so we're talking about some serious pressure. Then we got Type 2, which wrapped that metal tank in a composite material for extra strength, bumping us up to 300 bar. Type 3 was a big leap. A lighter metal liner inside a composite tank, pushing the pressure all the way up to a staggering 700 bar. And now, the state-of-the-art is the Type 4 tank. It's fully composite with a polymer liner. Incredibly light, incredibly strong, and also holding its 700 bar.
And wow, these numbers really tell the whole story. Just look at the gravimetric capacity. That's basically the weight of the hydrogen fuel you can store compared to the total weight of the tank itself. It jumps from a tiny 1.1% for a Type I tank all the way to 5.7% for a Type 4. That huge improvement in weight is exactly why cars like the Toyota Mirai can even exist. But as you can see, there's a trade-off. Look at that cost jump. Innovation definitely doesn't come cheap.
Okay, so we've figured it out for a car. That is a huge, huge step forward. But it begs a much bigger question, right? How do you scale this technology up to power not just one car, but entire cities, maybe even a whole country?
Yeah, for grid-level storage, the solutions have to be on a completely different scale. We're talking about moving from tanks you could probably lift to infrastructure that is literally geological in size. So let's look at the two big contenders for storing city-sized amounts of energy.
One solution is to get the hydrogen incredibly, unbelievably cold. We're talking minus 253 degrees Celsius. That is colder than the surface of Pluto. At that insane temperature, hydrogen gas actually turns into a liquid, and when it does, it becomes almost 850 times denser. That density is the whole key to transporting and storing it in bulk.
And you can really see the scale here. Just look at these massive spherical tanks at NASA's Kennedy Space Center. They can hold millions of liters of liquid hydrogen to fuel rockets. But there's this one persistent problem called boil-off. Because there's such a massive temperature difference between the liquid inside and the world outside, some of it is always constantly evaporating back into a gas. It's a slow but continuous loss of fuel.
But what if you could go even bigger? Way bigger. The most ambitious idea out there is to store hydrogen underground in these vast geological formations. You'd essentially be turning parts of the Earth's crust into a giant rechargeable energy battery.
So there are three main ways we could do this. We could use old, depleted oil and gas reservoirs. We already know they can hold gas under pressure for millions of years. We could use aquifers, which are these big, porous rock formations. Or, the one that has everybody really excited, we could carve out enormous caverns deep inside underground salt deposits. So why salt caverns? What's so special about them? Well, salt is incredibly stable, and it's almost completely impermeable to those tiny, slippery hydrogen molecules. That means these caverns can store hydrogen with up to 98% efficiency. It's amazing. There's a project happening right now in Utah to create a 300 gigawatt-hour storage facility. That's enough energy to power thousands and thousands of homes for months on end.
But compressing hydrogen into a tank or freezing it into a liquid aren't the only ways to do this. What if we could store hydrogen chemically as part of another molecule? This is truly the next frontier. And these technologies could completely rewrite the rules for how we move energy around the globe.
So this brings us to an amazing concept called liquid organic hydrogen carriers, or LOHCs for short. The easiest way to think about it is like a rechargeable liquid battery, but for hydrogen. In step 1, you charge it by chemically bonding hydrogen to a stable, non-flammable carrier oil. Then, whenever you need the hydrogen, you just gently heat that oil and poof, it releases pure hydrogen gas on demand.
And here's the absolute genius of this whole idea. Once the hydrogen is locked into that carrier oil, it pretty much behaves just like diesel or gasoline. That means you can transport it using the exact same infrastructure we already have today. Tanker ships, pipelines, storage tanks, you name it. A project led by a company called CGH₂ is already proving this works, shipping hydrogen all the way from Brunei to Japan using this method.
And this chart really drives home the economic advantage. When you look at the total all-in cost to ship hydrogen across an ocean, liquid hydrogen is by far the most expensive. Ammonia is another popular carrier, and it's quite a bit cheaper. But LOHCs, like methyl cyclohexane or MCH, actually come out on top as the most cost-effective. And this isn't just about saving money. A cost difference like this could fundamentally reshape global energy trade, allowing countries with tons of renewable sun and wind to become the new energy exporters of the future.
And finally, there's one more really fascinating approach: solid-state storage. The best way to picture this is like a high-tech sponge for hydrogen atoms. There are certain materials, like metal hydrides, that can physically absorb hydrogen atoms right into their own structure, and then they can release them later. It's a way to store hydrogen at much lower pressures and near normal temperatures, which could make it incredibly safe.
So, there you have it. We've got high-pressure tanks for our cars, massive underground caverns for our grids, and these incredibly innovative chemical carriers for global trade. Each approach has its own strengths, its own challenges. The race is officially on. And the real question isn't if we'll solve the hydrogen storage problem, but which of these incredible technologies will ultimately win out and power our future.